You have seen the photographs, the glowing vials, the blue light in the dark laboratory. Everyone has seen them, and everyone looks at them the same way, with wonder, with fascination, maybe a little romance about the early days of science. You think you understand what radium is. You do not. That glow is not a feature. It's not beauty. It's not magic. It is matter in the process of destroying itself and everything around it. What you're looking at in those photographs is an alarm bell that an entire generation mistook for a nightlight. I know this because I was one of them. I held it in my hands. I carried it in my pockets. I kept glowing test tubes on my bedside table because I found the light lovely. I was being taken apart at the cellular level the entire time. I didn't feel a thing. That's what we're going to talk about today. Not the discovery, not the Nobel Prizes. The actual question, the one nobody asked clearly enough, soon enough. What does radium do inside a human body? Not in metaphor, not in vague warnings, atom by atom, second by second. What is it actually doing? Let me start with something that still unsettles me when I say it plainly. I worked with radioactive materials for decades. My hands were chronically inflamed. My fingertips were damaged enough that I sometimes couldn't feel what I was holding. My notebooks, the ones I wrote my research in, are still radioactive today, not metaphorically, literally. They are stored in lead-lined boxes in Paris. If you want to read them, you sign a waiver. They will still be radioactive for another 1500 years, and through all of it, through the inflammation, the fatigue, the slow dimming of my eyesight, I didn't understand what was happening to me. Not because I was careless, because no one on earth knew yet. I was working at the edge of human knowledge, and the edge has no fence. But here's what makes it truly strange. The damage wasn't happening in any way the body could detect. There was no pain at the moment of exposure, no smell, no sensation of heat, no warning of any kind. You could be standing next to a significant radioactive source and feel completely, perfectly fine. The body has no sense organ for ionizing radiation. None. We evolved to detect heat, pressure, light, chemical signals, but not this. It's not like touching fire, where the pain is immediate and the lesson is instant. It's more like a thief who enters your house, takes nothing you can immediately notice, and comes back every night for 10 years, until one morning you realize the foundation is gone. So what is it actually doing? To understand that, you need to understand what radioactive decay really is, because most people have a vague sense of it, and the vague sense is wrong. Radium-226 is unstable, not in the way a chemical compound is unstable, where you can stabilize it with the right reaction or temperature. The instability is in the nucleus itself. At the very core of the atom, the structure is trying to rearrange into something that makes more physical sense. And when it does, when that nucleus shifts, it ejects matter, an alpha particle, 2 protons, 2 neutrons, traveling at roughly 5% the speed of light. That's not a wave. That's not an energy field in some abstract sense. That is a physical projectile moving through whatever is in front of it. And it cannot stop itself. It doesn't ask permission. It doesn't pause because you're sleeping or because you need a moment. It fires because the physics demands it, and it will keep firing in every atom of radium in a sample, according to a schedule set by the laws of the universe, not by anything you or I might prefer. The half-life of radium-226 is 1,600 years. That means if you had a sample today, half of it would still be decaying in the year 3626. The other half would take another 1,600 years after that. It is not a process that winds down on a human time scale, and once it's inside you, that clock runs inside you. Now here's where it gets specific. Here's where the biology becomes genuinely disturbing in a way that pure physics doesn't prepare you for. When radium enters the bloodstream, whether inhaled, ingested, or absorbed, the body makes a mistake. A catastrophic, well-intentioned mistake. The body looks at radium and sees calcium. They are chemically similar enough that the body's transport systems, the ones designed to route calcium to where it's needed, pick up radium and carry it to the same destination. The skeleton. Radium doesn't just pass through. It doesn't get filtered and excreted. It gets deposited into bone. And not just bone, bone marrow, the deepest, most biologically active tissue in your skeleton, the place where your red blood cells are made, where your immune cells are made, the place your entire blood supply depends on. From inside that tissue, every single decay event fires an alpha particle directly through living cells, through membranes, through DNA strands. And what an alpha particle does to a DNA strand is not a nick, not a scratch, it's a shattering. Double strand breaks, both sides of the DNA double helix severed simultaneously. The repair machinery inside the cell was designed to fix damage, but it was not designed to fix this kind of damage at this rate, repeatedly, without pause, originating from inside the cell's own neighborhood. The immune system doesn't flag it. The nervous system doesn't register it. The cell just tries to repair and repair and repair, and eventually it can't keep up, or it repairs incorrectly, and incorrect repairs are how cancers begin. Your body never knows it's under attack. It just keeps trying to function while the architecture collapses. We gave this a name, radiation sickness, and the name is accurate as far as it goes. But names are strange that way. They can make you think you understand something when you've only labeled it. Radiation sickness sounds like one illness. It isn't. It's a cascade of separate systems failing, each one failing for its own reasons, all connected by a single originating cause. The bone marrow gets damaged first, because that's where the radium concentrated. When the bone marrow fails, white blood cell production drops. The immune system goes quiet. Infections that a healthy immune system would eliminate in hours become life-threatening. Then red blood cell production slows. Anemia sets in. Real anemia, not tiredness, but a genuine deficit of oxygen carrying capacity in the blood. Fatigue becomes profound. Organs that depend on healthy blood supply start to strain. And then there are the delayed effects. Chromosome damage that didn't kill a cell immediately but altered it. That damage shows up years later, sometimes decades later, as leukemia, as bone cancer, as other malignancies that have no obvious connection to anything the patient can remember. No one connects the cancer in 1930 to the exposure in 1910. The arithmetic is too slow for human intuition. My own aplastic anemia, the condition that ended my life, was not the result of one bad day in the laboratory. It was the sum of years, quiet, accumulating, invisible arithmetic that my body was doing the entire time while I thought I was simply tired from working hard. The body does not die from radiation in one dramatic moment. It dies from losing, one by one, all the systems that radiation quietly dismantled from the inside. And yet, and this is the part I find most honest to admit, we don't fully understand all of it. We understand the mechanism I just described, the calcium-radium confusion, the bone marrow deposition, the alpha particle damage, the cascade of failures. That part is established. But there are layers below that, where the picture gets genuinely murky. We don't fully understand the threshold question. Why do some people exposed to the same dose develop serious damage, and others, apparently similar people, same exposure, same duration, show little to nothing, not immediately, and sometimes not ever? The variation is real, and it is not fully explained. There's something called the bystander effect in radiation biology. Cells that were never directly hit by a particle begin behaving as if they were. They signal distress. They change their behavior. They show damage markers, as if they received some communication from their injured neighbors. We can observe it happening. We can measure it. We do not fully understand the mechanism. We have working models. They are not proven laws. And low-dose radiation effects, the kind relevant to occupational exposure, to people who worked with radioactive materials over long periods, like my colleagues, like me, remain genuinely contested in radiobiology. The dominant model, the linear no-threshold model, says that any dose carries proportional risk, with no safe floor. It is a reasonable working assumption for setting safety standards. It is not proven. There are serious scientists who think the relationship is more complicated, possibly non-linear at very low doses. The debate is not resolved. I mention this not to make you uncertain about what is well established. The serious mechanisms, they're real, they're documented, they're the reason we have radiation safety standards. I mention it because I spent my career insisting on the difference between what we have measured and what we have assumed. That discipline is not optional in science. It is the whole point. Let me tell you what I've been circling around. My notebooks are in lead-lined boxes. My personal effects, the ones from the laboratory years, cannot be safely handled without protective equipment even now. I am, in some sense, still emitting, still present in the physical world as a source of ionizing radiation. Through the objects I touched, the materials I handled, the residue that transferred to everything I owned, I carried radium in my coat pockets. That is not a metaphor. I liked having it close. I thought the blue glow was extraordinary. I was right that it was extraordinary. I was wrong about what that meant. And I can say honestly that I was not ignorant. I was working at the absolute frontier of what human beings knew about matter and energy. The edge of the map. There is no fence at the edge of the map. There's just the edge, and then the unknown. And you proceed because the question is worth following. And you do your best with what you have. But there is something that happened alongside my work that was not about the edge of knowledge at all. The Radium Girls, the factory workers, mostly young women, who painted luminous watch dials with radium paint in the 1910s and 1920s. They were told to point their brushes with their lips, to put the brushes in their mouths to maintain a fine tip. Over and over, every day, ingesting radium continuously. They developed bone cancers. Their jaws deteriorated. They died in terrible ways. They were not working at the frontier of knowledge. The companies that employed them had access to enough information about radiation risk to have protected them. They chose not to. They told the workers the paint was harmless. Some supervisors knew better and refused to apply it themselves. What I just told you about how radium enters bone, how it fires into marrow, how the cascade of failure works, that is scientific. What was done to those women was not a scientific failure. It was a moral one. That distinction matters. It mattered then. It matters now. Every time a new technology moves faster than the willingness to ask what it might cost the people closest to it. The atom does not care. It has no intention. Radium-226 is not malicious. It is simply matter following the physics it was given at the beginning of the universe. It doesn't know you're there. It doesn't accelerate when you're sleeping or slow down when you're frightened. It just decays and fires and decays and fires at a rate set by forces that have nothing to do with human life. That indifference is not the danger. The danger has always been the gap, the space between what we know and what we assume we know. The moment when certainty outruns evidence, when familiarity gets confused with safety, when beauty gets confused with harmlessness, when a glowing vial gets called a miracle and no one asks what the miracle costs. That gap exists today. It exists in every laboratory, working with technologies whose long-term effects are not fully characterized. It exists in every excited announcement of a breakthrough before the follow-on questions have been asked. The specific element changes. The structure of the problem does not. I was one of the first people to hold radioactive material in my bare hands, unshielded, unprotected, with no full understanding of what I was holding. I would not change that. The work was worth doing. The questions were worth following. The science was real, and it mattered, and it has saved lives. But I would want everyone who came after me, in any field, with any new thing, to hold it with full knowledge of what it is, not to hold it less firmly, not to step back from the frontier, to step forward with open eyes. The mystery of what radium does inside a human body is not completely solved. We know more than my generation did. We know the mechanism, the cascade, the calcium confusion, the bone marrow catastrophe, the delayed cancers. We know it well enough to protect people, which means what happened to those factory workers was preventable, and that is its own kind of weight to carry. What we don't know is still real. The bystander effect, the threshold variations, the low-dose questions that good scientists still argue about. The biology is more complicated than any clean model captures. That should not frighten you away from science. It should pull you further in. The questions that remain are not signs that science failed. They are the proof that it's still alive. I spent my life at the edge. I'd do it again. The light was extraordinary.